you again for inviting me back, and welcome to all of you. This is the second half. Last week I talked more about concepts and designing studies, the different types of studies that would end up with correlated data. This time, unfortunately, it's going to be a little bit more technical, more on the statistical side. A lot of what I'm going to be doing today is a good news, bad news type of dichotomy. Bad news here is that it's going to be a bit more technical. The good news is the reason for bringing in the technical is because you can actually run these analyses. Up until maybe 15, 20 years ago, there wasn't much software around, and so hearing about the concepts was useful, but not as useful as if you could actually run the analysis. So nowadays, journals will expect you to account for correlated data. There's software routines within most of the major programs, Stata, SAS, R, that will allow you to actually carry out the analysis. So that's sort of the good news. Bad news, again, being that you're going to have to make the choice and understand a little bit about what the software is going to require from you. But the good news is that the software exists, and it's not a lot of information, not a lot of input that you need to give. The other part of the good news is once the program has run, adjusting for the correlation for the dependence becomes entirely transparent to you. The results will look like ordinary regression results. And so if you're comfortable with regression, you'll be very comfortable with doing longitudinal analysis with just, again, as I said, minor changes as far as what you have to tell the program. So what I want to talk about, how you incorporate correlation into an ordinary regression model. And there's, again, the bad news is there's two ways to do it. The second bullet, marginal models, is one approach. Within marginal models, you're going to have to specify the correlation structure, and I'll show you what that means. And then I'll show you an example of where we go through all the steps and run the analysis, and how much really the correlation structure matters, which the good news is it doesn't matter that much. Bad news is you still need to specify it, so that much you have to understand. The other bad news is marginal models are not the only approach. There's a different approach called conditional models. Not that you have to use them, but at least you have to understand that there are different approaches. And so if you're reading a journal, it helps to be able to recognize at least the terminology. And if you're submitting into a journal, if they ask you questions of what sort of model, how did you account for correlation, again, having at least these two words, I used a marginal approach or I used a conditional approach, will help orient the reviewers and the readers. The good news, again, is whether you use a marginal approach or whether you use a conditional approach, the answers are often quite similar. They're definitely interpreted the same, but they're also numerically very similar, and I'll show you an example of that. So while you need to know how to approach it, the good news is that the answers really are not very sensitive to the approach. So very, very quick review, a regression model. This is the same model that I looked at last week. So the outcome are CD4 counts. For today, I'm just going to worry about two predictors, time, so to see how the CD4 counts change over time, and gender, to see whether CD4 counts differ between men and women. You can have in your model as many predictors as you like. I'm using time as continuous, so beta 1 represents a slope over time. If you want to use time via indicator variables, so that over time you can have bigger steps up or down, that's perfectly fine. I'm just keeping my model simple for the sake of the exposition today. Like I said, you can have as many variables of different types, categorical, continuous, binary, as you like. When you build your longitudinal regression model, all the same principles apply. So Variables that might be collinear will fight each other for power. Confounders will change the coefficients. So whatever you were comfortable with in terms of building a regression model, all of those same principles carry over. There's, like I said, only going to be minor changes in our final interpretation, but most of the model building carries over entirely. For a usual linear regression model, we assume that these epsilons, the error terms, are independent random variables. And if the epsilons are independent random variables, the CD4 counts, our outcome, is also independent. It's a random variable. If the epsilons are normally distributed, the CD4 counts are normally distributed. And what we want is the software program to estimate how time affects CD4 counts and how gender affects CD4 counts. So beta 1, the coefficient for time, tells us for every unit change in time, and I'm measuring time in months, CD4 counts will go up or down by beta 1. And for comparing men to women, a binary predictor, beta 2 is the difference in CD4 counts between men and women. These are unknown numbers, but when we run the software, we'll have estimates for beta 1 and beta 2. And I'll show you in a minute what the results look like, but we'll know what the relationship is between time, gender, and CD4 counts. For linear regression with independent outcomes, there's really only one way to approach the fitting process. There's two names. You can call it maximum likelihood or you can call it least squares, but the algorithm is the same. The answers will be the same. The standard errors will be the same, p-values, confidence intervals. You can run this program in Stata, you can run it in SPSS, you can run it in SAS. For simple linear regression, you'll get the same answers, same approach, same answers. You don't really have to explain what you did to reviewers. You ran a linear regression. That explains it all. However, when it comes to correlated outcomes, as we have with the CD4 counts, they really are not independent because each person has 3 measurements and those CD4 counts will be correlated. Dependent was the word I used last week. This week it's going to be more statistical, and so instead of the word dependent, I'll stick with the word correlated. And how do we bring the correlation into the story? 2 ways. As I mentioned, there's marginal models, conditional models. With a marginal model, we're going to bring the correlation in by allowing the epsilons to be correlated with each other instead of being totally independent of each other. A conditional model approaches the same problem but in a very different way. Instead of having the epsilons correlated, we're going to change the coefficients in the model to be random variables. That will create the correlation, and that's what we're going to look at last. The conditional models are usually a little bit harder to fit. If your software has limits, the conditional models will be the ones that won't be there or won't run. And so we'll start and spend more effort, more attention on marginal models. But eventually, you'll see that the approach breaks into these 2. And again, when you say in your method section, we use software that allowed for correlated measurements, you should qualify that with we used a marginal model or we used a conditional model. And I would like to tell you that these are your 2 choices, but unfortunately it does get more complicated. Not for today's lecture, but in real life, there are a couple of different approaches for marginal models, a couple of different approaches for conditional models. So while these are the 2 big classes, the first decision you need to make, within the class, there are also some minor choices to be made. So without worrying about the minor choices, how do you choose between these 2? Partly it's philosophical. So I need to sort of show you both approaches, and then we can come back to this issue later on. Just a matter of really purely your preference philosophically. how to incorporate the correlation. It's also partly practical. So when you look in the literature, longitudinal data, very often people use marginal models. The conditional models are often used for cluster data. I introduced the notion of cluster data last week. So longitudinal data is sort of easy. You have repeated measurements over time on each individual in your study. The correlation comes through the fact that each person is measured multiple times. Cluster data meant something like we were looking at patient outcomes, whether a patient lived or died, the quality of life, the function of the patient, but those patients were treated by a number of physicians. And so the patients are clustered within their treating physician. Patients who are treated by the same physician will tend to have dependent outcomes. Patients seen by different physicians tend to have independent outcomes. And so that's what I meant by cluster data. And it turns out that when you look in the literature, when you have cluster data, you'll often see a conditional model used. That does not mean that you have to follow these conventions. But if you just want to rely on sort of historical precedent, this might give you a clue of which direction to go in. Partly too, the choice is driven by the software you have. As I mentioned earlier, nowadays, most major software programs allow you to choose your approach. There'll be a different routine for marginal versus conditional, but they'll both be there. So first question, can your software fit marginal models? Answer is usually yes for all the major programs. Can your software fit conditional models? And the answer is usually yes for linear regression, so a continuous outcome, but not always yes for logistic regression or non-normal outcomes. So again, marginal models are better developed in software, conditional models less so. And so I don't know if this should drive your choice, but sometimes it certainly influences your choice. If you can't run a logistic regression using a conditional model, then go ahead and run it using a marginal model. It's perfectly fine, and you're just being practical about what's available to you in the software. And as I said, it's also the choice is driven by precedent. So in your field, in the journal that you intend to publish, what have other people done? Because your reviewers will be more comfortable if they see precedent. And again, you can look in your specific journal. My general feel is that marginal models are going to be more common since the software was developed earlier and therefore became more widespread. So again, this isn't a good scientific reason for using marginal models, but it is a practical one. And like I said, marginal model, conditional model produce very similar results in the end. And so choosing an approach which reviewers are more comfortable with is not a bad idea. So the choice is yours, though. So these are some issues, but the final choice is definitely yours. Most of the points I've made drive you towards a marginal model. And so that's where we'll start. Again, emphasizing that the results will be similar, and I'll show that to you at the end. But we'll start with marginal models for a number of the reasons that I showed you. This time, again, I'm using sort of the more sophisticated notation since we are going to deal with correlated data. There's two subscripts. The first one identifies the person. For CD4 counts, there were 103 subjects in the study, so I goes from 1 to 103. J refers to the time point. This is longitudinal data. I had 3 measurements per patient. J is 1, 2, and 3, but you can have as many as you like for each person. But that's the reason for the double subscript. It's identifying 2 different things. The usual assumption for a marginal model is that these error terms, the epsilons, and therefore the outcomes, are independent over I, and it's better to substitute in the words. So my outcomes, my measurements, are independent across subjects. different people. Their CD4 counts are independent. My CD4 count is independent of yours, is independent of everyone else in the room. We have independence over subjects. But the epsilons, and therefore the outcomes, are correlated, dependent over J. So J was time. So my CD4 counts are correlated over time, but independent over people. So my CD4 count does not influence your CD4 count, but my CD4 count at baseline is going to be related to my CD4 count at 6 months and 12 months. So if my CD4 counts are relatively high at baseline, they probably will be relatively high at follow-up as well. So this is not the only set of assumptions, but for longitudinal data, this is certainly the typical set of assumptions. And now we have outcomes that are correlated, and we can use software that recognizes that. That was the hard part of the discussion, the correlation that comes in through the assumption about the epsilon, the error terms being correlated. The friendlier part of this model is when you look at beta 1 and beta 2, they represent the same things that they did in an ordinary regression. So each beta still represents the effect of the predictor on the outcome across everybody in your study. So there's a special wording because we need to distinguish it from the conditional models. Beta 1 is the population average effect of the predictor on the outcome. Fancy word that doesn't really mean a whole lot. It just means that if X1 is time and Y is CD4 count, beta 1 is telling us how in the overall population CD4 counts change with time. And we're assuming that beta 1 represents everybody. So it's not just my CD4 count changing over time or yours, but it's everybody's. Same thing, beta 2 represented the difference between men and women. It's not between a particular pair, but it's between all men and all women. So this sort of population average effect, and making it more concrete, this is my longitudinal model for the CD4 counts. Sorry, there should be 103 people. You'll see that a little bit later, not 101. But I represents the person. J represents time, where 1 is baseline, 2 is 6 months, 3 is 12 months. In this model, the intercept, whether you call it beta naught or alpha naught, is the baseline CD4 count for men. So if you remember your interpretation of regression, the intercept is the predicted outcome when all the covariates are 0. So when time is 0, we're talking about baseline. When gender is 0, the way it was coded in this data set, we're talking about men. So the intercept is the baseline CD4 count for men. Beta 1 is the slope over time. So as time increases month by month, CD4 counts change by beta 1. Beta 1's positive, they go up. Beta 1 is negative, they go down. We assume that the slope is the same for everybody. When you look at a person's actual data, it may not show exactly this slope, but it's being estimated to be beta 1 plus minus noise for everybody. And beta 2 is the difference between CD4 counts in men and women. And when you compare these interpretations to the interpretation for a simple regression without correlation, it's exactly the same. And when we fit the model, this is what the picture would look like. We have CD4 counts at baseline, at 6 months, at 12 months. We put together a regression model where there's a slope for men and women and a very small difference between men and women. The red and blue lines represented pictorially on the last slide, but running it, this is the result. CD4 count equals 500, that's the intercept. So that's where men start from. 17.3, the same slope for men and women. So CD4 counts increase by 17.3 cells per month. That estimate has a standard error of 2. You can take the ratio, get a t-test and a p-value. You can take the estimate plus or minus 1.96 standard errors and get a confidence interval. But this is how CD4 counts change over time for everybody represented in this population. And 16 is the estimated coefficient for gender. It's the comparison between women and men. Women have slightly higher CD4 counts, but the estimate is unstable, has a large standard error. The ratio, the T, is non-significant, and so men and women basically have the same CD4 counts, and they're increasing significantly over time. If you just consider the bottom part of this slide, the equation with the estimates plugged in, the estimate, standard error, p-value, and confidence interval, if you like, and think about how this differs from just an ordinary linear regression. I'm hoping that you recognize there's really no difference. The equation is interpreted, turned into p-values, turned into confidence intervals in exactly the usual way. The fact that my software program recognized correlation over time between these epsilons is totally transparent to you when it comes to interpretation. So the good news is, as long as you know that these are correlated, and you should use a software program that recognizes the correlation, once you run it, the results look just the same as usual. And if you worry that there may be other things happening with time, that this is confounded, put those variables into the model. If you think that males and females, that there's other confounders as well, put those into the model. If you're interested in other predictors, put them into the model. The results are going to be just as interpretable with this model, with the correlated epsilons, as they were with ordinary regression. So once you run the right routine, the good news is there's really no trick to interpreting the results. They're just like any other regression model. What did the program do to deal with these? If you cared, you could go through the literature, figure out how the algorithm works. Most people don't care as long as they know it's been dealt with correctly and what their software program required in order to understand how to deal with these. And that's really sufficient for us. The important part is building the right model and interpreting it. We rely on the software to have dealt with the correlated epsilons appropriately. And so, back to that. The only thing new about this model were the epsilons. This was, again, the structure, the people, and the time points. Correlation structure says that the correlation between epsilon 1j and 2j is 0. First index is for the person in the study, and we've already said we don't believe that the CD4 counts from one patient are correlated with the CD4 counts from a different patient. So this correlation being 0 just repeats the assumption that CD4 counts are independent across people in the study. The second bullet, though, says that the correlation between epsilon I1 and I2 is not 0. And if you like, I've taken these epsilons and translated them into CD4 counts. So the correlation for patient I between their baseline CD4 count, that's what J1 represented, and that same person's 6-month CD4 count, that's not 0. That's equal to, this is pronounced rho, 1, 2, because it's between the first time point and the second time point. So J being 1 and 2, we're assuming for a given person, there is correlation over time between baseline and 6 months. So between people, no correlation, but within a person over time, there is correlation. Correlation coefficients go between minus and plus 1. For CD4 counts over time, I would imagine this is a positive number. I imagine it's greater than 0. I don't think it's 1. I don't think CD4 counts don't change over time. They do. But I imagine that there's some degree of positive correlation over time. And here, I've said baseline in 6 months. There are actually 3 measurements. And so I'm going to expand and say between baseline and 6 months, there's this amount of correlation. That's some number. Between baseline and 12 months, there's a different correlation, so different notation. Still rho, the correlation, but between baseline and measurement 3, which is 12 months. And then, of course, there's correlation between the 6 month and 12 months. 6 months was measurement 2, 12 months is measurement 3. And so, again, the notation that's typically used, you don't spell it out with the words. You can if that makes it clearer. But the shorthand notation is that the correlation between the first and second measurement, first and third measurement, between the second and third measurement. And I suspect that these are non-zero. The good news, again, is if they are non-zero and you're using the proper software, your software will actually estimate how large these are and adjust for them, so that if I go backwards, these estimates, the standard errors, and therefore the p-values, are actually adjusted for whatever correlation was present in your data. If there's no correlation, there was no adjustment. If there's positive correlation, it's been adjusted for. If it's a large correlation, it's been adjusted for. So you don't have to know what the correlation is. If you ask your software nicely, it'll actually tell you what these numbers are. If you don't, they're built into the calculations anyway. So again, it just comes down to using the right piece of software that allows for correlation over time, but still treats people as independent. So as long as you inform your software about the structure of the correlation, the software will estimate how much correlation there is. When we get to more than 3 measurements, there gets to be a lot of correlations, and so the presentation is through a correlation matrix. So the numbers that I showed you on the last slide were row 1, 2, 1, 3, and 2, 3. So between baseline and 6 months, this is the degree of correlation. Between baseline and 12 months, this is the degree of correlation. Between 6 months and 12 months, this is the degree of correlation. So conceptually, I think this is easier, but when you get to 5 or 10 different time points, there's just too many correlations to list. And so the convention is to think about them, present them in terms of this sort of matrix. On the diagonal, it's the correlation between a measurement and itself, and so that's equal to 1. I put the generic notation in here, but really there's 1s on the diagonal because everything has a correlation of 1 with itself. And the correlation between baseline and month 6, or between baseline and month 6, are the same. So these two numbers, even though the subscripts are reversed, the numbers themselves are the same. This and that are the same, this and that are the same. And so in this matrix, there's actually only 3 numbers that are of interest. These repeat on the diagonal are 1s, and so we really focus on the upper diagonal and say that there's 3 numbers, 3 correlations that your software needs to address before it can run the model. But that's actually the good and the bad news. Again, here there's only 3 numbers. But remember, we were interested not in these correlations, we were interested in the effect of time and the effect of gender, 2 estimates. And your program needed to estimate their standard errors. Now I'm saying that your program also needs to estimate 3 correlations. Anytime we ask more of your software program, all of the estimates are going to become a little bit more unstable. And so by estimating these correlations, we make the estimates of the betas a little bit less stable. We steal a little bit of power. And so working with longitudinal data, while this part may be transparent to you, it does really affect the results that you see. And so there's a question to ask you. These are the numbers I can actually show you for the CD4 counts. Baseline to 6 months, there's a moderately strong correlation, a little bit weaker between baseline and 12 months, between 6 and 12, again, a similar sort of correlation. 0.53 repeats, 5.1 repeats, 6.9 repeats, and certainly ones on the diagonal. So these are the three numbers that are of interest for the CD4 counts. There's a moderately strong correlation as you measure CD4 counts over time. This is what I was alluding to, though, as a worry. My study was relatively small. What if you have baseline and 4 follow-up measures? Now the correlation matrix starts to get larger. And now instead of just estimating 3 numbers, when I count these in the upper diagonal, there's 10 numbers that need to be estimated. I may still only be interested in the effect of time and gender, 2 betas, but in order to get those 2 betas, my software program has to estimate 10 correlations. The more things it has to estimate, the less stable everything becomes. And so the question to you, and I'm posing it to you because your software will ask you the same question. If you're going to run a longitudinal analysis, what type of correlation matrix do you want to use? And this one that I'm showing you here is called an unstructured correlation matrix. This term, unstructured, is pretty common now, so whether you're using SPSS or SAS or Stata, the notion of an unstructured correlation matrix kind of cuts across the programs. Here, if you say unstructured, and quite literally, when you run it, you'll say something like type equals unstructured. And that's pretty much the only input you're going to need to give it, and then you'll get answers. But if you say unstructured, your program will need to estimate the correlation between baseline and 6 months, between baseline and 12 months, baseline and 18, baseline and 24, and all the rest of these numbers. It will need to estimate 10 correlations before it can give you the beta for time and the beta for gender. It's doable if you have enough data, but it is going to take power away from your estimates of the betas. And so let me ask you, for this sort of study, a longitudinal study, would you be willing to live with a simpler correlation matrix? So for the previous one, the instruction to the software would have been to write the code type equals unstructured, or make the choice type equals unstructured. What I'm asking you now is, would you be willing to tell your software type equals toplets? That's how this is pronounced, toplets. And what you'll see here is the baseline to 6 months. There's a correlation, I called it row 1. Between baseline and 12 months, there's a different correlation. It can be weaker or stronger. Row 2, baseline in 18, row 3, baseline in 24, row 4. But when you go here, month 6 to month 12, I have the same symbol here as here. What I'm asking you to believe, to assume, is the correlation between baseline and 6 months is the same exact number as the correlation between 6 months and 12 months. If you're willing to make that assumption, what you'll see is there's only 4 numbers that your software needs to estimate. Here, there were 10 numbers that your software needed to estimate. If you put less burden on your software, only estimate 4 correlations, that means that your estimates of the betas for time and gender are going to be more stable and have more power. So by doing less here, you save more of your power for estimating the coefficients you care about. The cost of that is assuming that these 2 correlations are the same. Previously, I let them be different. Why would I assume that these 2 correlations are the same? Baseline to 6 months is the same as the correlation from 6 months to 12 months. Argument is, this is the CD4 count at one time point. This is a CD4 count 6 months later. This is a CD4 count at one time point, and this is a CD4 count 6 months later. And so row 1, if you like, represents not baseline to 6 months and not 6 to 12. Row 1 represents the correlation between two CD4 counts measured 6 months apart. This is also 12 to 18, CD4 counts 6 months apart. This are CD4 counts 6 months apart. So if you like, row 1 represents the degree of correlation between two CD4 counts from the same person measured 6 months apart. If you think that 6 months is the key point, not which 6 months, then I just plug in one number for all 4 entries. Row 2 is the correlation between CD4 counts that are 12 months apart, whether it's base to 12, 6 to 18, 12 to 24. Row 2 is the correlation CD4 counts on the same person 12 months apart, 18 months apart, 24 months apart. This puts less burden on your software program. And what does the burden matter to you? Well, again, it goes back to here. You didn't care about the correlations, I'm betting. You cared about the model and its coefficients. And the less the program has to do internally for correlations, the more stable your estimates of the betas are. And so if you're willing to make this assumption, which is not an unreasonable one for longitudinal data that's equally spaced, so everything is 6 months apart or 3 months apart or 12 months apart, Toplitz is a nice simplifying assumption that buys you power. And if you're willing to go in this direction, then let me make one more possible suggestion. Rather than saying type equals unstructured or type equals Toplitz, how about type equals autoregressive? The abbreviation here is AR or AR1, but again, this tends to be a standard option in most software packages. Rather than a complicated correlation matrix, this is the one that's being suggested, if you're willing to make this assumption. Between baseline and 6 months, the program will estimate the degree of correlation. And then baseline to 12 months, this is not a typo, it's not rho sub 2, this is rho squared. So if the estimated correlation was 0.5 between baseline and 6 months, the correlation between baseline and 12 months is 0.5 squared, 0.25. And between baseline and 18 months, 0.5 cubed is 0.125. And between baseline and month 24 is 0.5 to the 4th power. This is saying that the correlation diminishes geometrically over time, which is not an unreasonable assumption. We would expect the further apart CD4 counts are over time, and again, this has nothing particular to do with CD4 counts, any physiologic measurement. So blood pressures, if you measure them 1 day apart, the correlation is very high. 1 month apart, the correlation is lower. 1 year apart, lower still. Blood pressures measured on the same person 10 years apart are probably going to have a correlation that's virtually 0. And that's what this does. This allows the correlation to decline geometrically. 6 months apart, it's always rho. 12 months apart, it's rho squared, and so on. The beauty of this assumption is you only need to estimate one number, U. The program only needs to estimate one number, and then the rest of the matrix is filled in. And so it's a very parsimonious model, which means you don't spend a lot of power estimating the correlation. You have that power to estimate the betas for the predictors. Again, you need equally spaced. You need to make this assumption. If the assumption is not true, that's going to be a problem. One more, and then we'll get to sort of the trade-off. This correlation matrix, also, you only need to estimate one number, and it gets filled into every single slot. So would you expect the correlation between CD4 counts 6 months apart to be exactly the same as between CD4 counts 12 months apart? exactly the same as between CD4 counts 18 months apart? I would hope your answer is no. I would expect the correlation to decline over time or to change over time, but I wouldn't expect it to be exactly the same over time. So this, again, has a name, exchangeable, and also compound symmetry. They're synonyms. This would not be a reasonable model for a longitudinal study. But if you have cluster data, and these are not time points, but patient 1, patient 2, patient 3, patient 4, patient 5 within the same physician, the correlation between patient 1 and 2, or between patient 1 and 3, or between patient 2 and 3, is very often assumed to be the same, because those patients are not sequential in time. They're just different patients seen by the same physician. They're exchangeable. So this is actually a very popular type of correlation matrix, but for cluster data, not for longitudinal data. So again, it's a standard choice, but one you should not make for longitudinal data, but it gives you a sense of there are better choices and worse choices. And if you don't want to make any assumptions, just go with unstructured. But your software may need to estimate many correlations, makes the betas unstable, and loses power. So if the betas are unstable, it means they have large standard errors. It means your p-values will be larger. If you're willing to make a choice, make an assumption about a specific correlation structure, and you choose correctly, then the program has to estimate fewer correlations, and you'll have better power left over for your betas. Of course, if you choose incorrectly, you won't get valid results. So this slide puts you basically in the driver's seat. You get to choose. It's very much like choosing a non-parametric test versus a parametric test in a lot of analogies. If you're willing to choose a specific correlation structure, if you're willing to make an assumption, so if you're willing to assume that your data follow a normal distribution, you should run a t-test. If your data really are normal and you run a t-test, that t-test will have optimal power. But if you assume normality and the data really aren't normal, you've chosen to do a t-test, which gives you invalid results and lots more false positives. If you're hesitant about making an assumption, you could fall back on, I'm not going to assume anything about the data. I'll run a non-parametric test, a Wilcoxon test. That's always safe, but may not have good power. So if you think about that analogy, it may help put this into sort of perspective. When you're going to run an analysis, a regression analysis, and there's dependent data, you can play it safe. Just assume unstructured correlation. The data will drive all the choices, but you may lose some power. If you think you have a good sense of what the correlation structure will be, you can specify that. Toplets, autoregressive, that'll save you power and give you better estimates of the betas. So it depends on whether you're willing to make an assumption, gain power if you're right, or you'd rather not make an assumption, give away a little power, but be safe in all cases. Okay. So back to our CD4 counts, same structure of the model, independence over people, dependence over time within person. I need to choose a correlation matrix. I need to tell my software what sort of correlation, unstructured, autoregressive, toplets. I've already decided that exchangeable is not reasonable for this situation. And I need to set up my database in this format so that I can tell the software, look in the variable, the column called subject, anybody that has the same value, those are correlated measurements, times 6, 0, 6, 12. Here's another threesome, and the correlation between those three measurements is going to be estimated according to this matrix with an assumption thrown in or not. Those are actually the only two things you need to do to run a longitudinal regression model. Set up the database this way so that there's a variable that tells the software which variables, which measurements are correlated. These three are, these three are, these three are, but these CD4 counts are independent of those three, are independent of those three, because they're from different subjects. And when I say they're correlated, the program will estimate the degree of correlation, but whether there's any structure to the correlation is up to you to specify. So again, play it safe, say unstructured. There's only 3 numbers to estimate. Seems pretty reasonable. If you had more follow-up time points and you didn't have a big data set, maybe you want to preserve the power, you might say autoregressive or toplets. With these 2 slides, that's it. Your software program needs to know this much: what sort of matrix and how, which variables, which outcomes are correlated. You're set to run. So here's my CD4 count data. I wanted to run a linear regression. Here's the structure of the data. They look, the CD4 counts, at least roughly normal, so linear regression seems fine. I need to specify the correlation matrix. How should we think about it here? This is a longitudinal study, evenly spaced data. So we could call it unstructured, but we could also call it toplets. We could specify autoregressive. I would expect the correlation to decrease over time. So values 6 months apart would be more highly correlated than values 12 months apart. So still, unstructured, autoregressive, or toplets might be reasonable. Exchangeable would be unreasonable. It wouldn't allow the correlation to decrease. A moderately large sample size, so 103 people, so I'm not going to have too much power loss, even if I specify unstructured. And most of the subjects have all 3 time points, so I should have stable estimates of the correlation. Again, 3 choices: unstructured, autoregressive, toplets, would be standard choices for any software package. Given that I have sufficient data and only 3 time points, personally, I'm kind of leaning towards unstructured. I don't like to make assumptions unless I have to. Here I've got plenty of people to estimate only 3 correlations. I would go with unstructured. These would not be wrong choices. They'd be reasonable alternatives. And again, if you're thinking about who's going to make this choice, it's going to be you. These are all reasonable. Which one you choose is up to you. I doubt if you're even going to specify in your method section what you did. The readers will trust to you making a reasonable choice. As long as you mention that you adjusted for correlation, they probably will not ask how. It's just the fact that you did. So step 4, build, run, interpret your model in the usual way. Once you have the right software and you've set up your database correctly and you've made your choice on what to declare the correlation matrix to be, you run it. And here are the solutions that I got. You should not be running it 4 different ways and then choosing the answer you like. You should be choosing a reasonable approach and then reporting the answer. But I just wanted to show you what difference this made. So CD4 counts, I use what's called restricted maximum likelihood and tried it assuming independence. Independence is clearly wrong, but I just wanted to show you what the answers were. There really should be dependence over time. I showed you the correlation matrix with moderately strong correlation. And so whether we let the software run it as unstructured, whether I tell it to estimate fewer correlations and just call it toplets, or estimate just 1 correlation and let it decline geometrically over time, what you'll see is the intercepts are really virtually the same. standard errors for the intercepts are virtually the same. The effect of time is someplace between 17 and 18 per month, an increase in CD4 count of 17 to 18. It really didn't matter. The only place where it mattered is in the standard error for the slope. So with independence, this is, if you remember from last week, a within person effect. We actually gain power by running it the right way. Which way we specify the correlation doesn't matter very much as long as we allow for some correlation. As you can see, we really get very similar results, which is great. And then what's the effect of gender? Again, this is a non-significant effect, and so while it bounces around from any place from -10, women have lower CD4 counts to women have 16 point higher. This is all within the range of noise, and so from all of these models, we conclude that there's no gender difference in CD4 counts. What you will see, again, the big difference is if we assume independence, we're underestimating the standard error. If we allow for correlation, the between subject effect has a larger standard error, just like theory would predict. Again, not so much larger that the p-value makes much difference, but to get the standard error correct here and the standard error correct here, we really need to allow for some degree of correlation. The actual structure didn't matter. And so the good news is, if you go no further than this lecture and you choose to use a marginal model, you know that you're going to have to specify a correlation structure. If you don't, it will probably default to unstructured. And now you know a little bit about what it means by correlation structure. And the answer is not going to change very much no matter what you choose. If the answer does change and you want to know which of these is really the best, if you run it using the approach I've suggested here, there would be another number on your printout, the AIC, Akiyiki Information Criteria. And of these three models, the one with the lowest AIC would be the one with the best chosen correlation structure. So we haven't gone to that level of detail in this lecture, and I won't for the sake of time, but it's nice to know, you can sort of store it away in your notes and in your mind, that if you really want to compare these three approaches, you can. There'll be a single number printed out on each printout, the AIC. One with the lowest one is the best assumption for correlation structure, and that can point you to which one you should use. Personally, I think if you think it through scientifically, you can choose a priori the one that's reasonable and just live with those results. But it is possible to actually compare correlation assumptions quantitatively. But as I said, the good news is our conclusions are certainly the same, and even our answer quantitatively, how much does CD4 count change per month, is pretty much the same answer regardless of approach. So, any questions here before I move to the other branch? These were marginal models. Really, the only thing that you had to do was set up your database the correct way, and then use the right software where it's going to ask you one thing: what sort of correlation structure should it assume? Where the default, I would imagine, is unstructured, but you have some ability to make a choice which could improve your power.
John,
Any
may I ask
questions
a question?
before-
AIC, what does it stand for?
Say again?
AIC, what does it stand for, the abbreviation?
Oh, it depends. Most people would translate it into the Akiyiki Information Criteria. Akiyiki is a Japanese statistician who proposed it. And it's spelled exactly like it sounds, although I wouldn't try to do it real time. A-I-K, anyway, with K's and I's and E's. If you asked him what it stands for, he would say it stands for another information criteria.
Okay. All right.
So the AIC also comes into other sorts of regression models. Because of the way this was fit, lowest value for the AIC would give you the best correlation structure. If you like, you can just go to logistic regression. I'm betting your program would print an AIC for a logistic regression. And if you're comparing different models, should I use age as continuous? Should I use age as categorical? The model with the lowest AIC is the best model. So AICs are useful for many things for choosing best. Best meaning lowest AIC. It would not mean that it's significantly better. But if you have a simple question, I want to include age, should I use it as continuous, binary, or 4 categories? Run the 3 models, choose the one with the lowest AIC. Here I ran 3 different correlation structures. The one with the lowest AIC would be the best choice for correlation structure. So AIC has sort of a broad use, becoming more and more popular, especially for things other than linear regression.
Okay, great.
Okay?
Thank you.
Any other questions before I complicate the story?
One question.
Sure.
Hello, doctor. Sorry, I don't know if I missed it, but as I see these comparison, I don't see a big difference as an amateur. I'm not a statistician, but I don't see a big difference between the independent model and the other model, right?
Yes, correct.
So what is
That's
my
good.
benefit of doing this approach? Besides, probably as you told us last time that we would win in terms of sample size, we can save in terms of sample size.
Well, 2 things. One is the reviewers will accept your paper, so purely from the practical side. It was funny, 20 years ago, you could get away with just running it as independent. Now there's no way that you'll be able to publish a study with longitudinal data where you have not used some sort of method to deal with correlation. So at the very least, if you intend to publish, no matter, you can't argue it's not going to make much difference. They are going to argue, but the software will run a correlated data model. You need to do so.
Sure.
So that's one very practical argument. The other is that here the effect of time is so strong that I can't really impress you. But if you notice here, the standard error is 2.7. Here the standard error is 2. And so if you like, the standard error is about 30% smaller. And if the test, the p-value, is simply taking the estimate divided by the standard error. If you can make the standard error 30% smaller, the ratio gets 30% larger. And sometimes when the ordinary regression gives you a non-significant result, the longitudinal regression will give you a significant result. So that's an important gain. Again, I'm sorry I can't demonstrate it here. They're all so highly significant. But there will be occasions when this p-value is 0.06, 0.07, but this one will end up being significant. And I hate to say it, but again, publication-wise, journals like significant results. Not almost significant results, but significant results. And so having the best power possible, even if I don't need it today, knowing how to get it next week is important.
Sure. Thank you.
Sure. Okay. I will switch then. These were marginal models. the correlation was accounted for through the epsilons and through that correlation matrix. What I'm switching to now are conditional models, so a different approach. You can use them for longitudinal data. Some people do. They have an appeal that you may find immediately. Many people use them for things like nested data, so health services research, patients nested within physicians, within hospitals. It's just an alternative way to allow for correlation or dependence. So this is now the equation. Structure is the same. I is still with the subjects. J is still specific time points. I'm still going to use this model for my CD4 counts for longitudinal data. But the big difference, the noticeable difference is here and here. Instead of alpha, this is now an A. Instead of beta, this is a B. And for statisticians, this is an important distinction. If I'm using Greek letters, these are called fixed effects. If I'm using Roman letters, these are random effects. And because I have some Roman letters and some Greek letters, this is a mixed model. I'm mixing fixed effects along with random effects, and so it's a mixed model equation. Not only is this a Roman letter, it now has a subscript. And so AI refers to the intercept for the ith patient. BI is the slope for the ith patient. So previously, the model was just alpha naught and beta 1. The effective time was beta 1. It was the same effect for everyone. But now the effective time is for the individual. Everybody has their own intercept and everybody has their own slope. And the epsilons are back to being independent. So for a marginal model, I work with the epsilons to introduce the correlation. With a conditional model, the epsilons are back to being independent across people and across time, and the correlation is captured through AI and BI. And so let me try a couple of times to explain what they represent. So AI is a random variable representing the baseline CD4 count for patient I, and we're going to assume that these A's follow a normal distribution. B is a random variable representing the effective time for patient I, and they follow a normal distribution. Beta 2 is like it was before. It's just the difference between men and women. It has no subscript I. It's just purely the difference between men and women. And so instead of alpha naught and beta 1, we have random variables representing the different people in the study. Making it more personal, if I just drop the gender effect just for simplicity, patient 1 has this equation. CD4 count for patient 1 is A1 plus B1 times time. Patient 2 has an equation A2 plus B2 times time, and so on. Each person, if you like, has their very own equation, and this is how I'm picturing the data. Every person starts at a different point. Those are my AIs. And each person has a different slope. Those are the BIs. And so if you like, when I run this model, I won't have one slope telling me how time affects CD4 count. If there's 103 people in this database, there will be 103 slopes, and there'll be 103 intercepts. Everybody has their own personal model. And so here's where the philosophy comes in. What do you think about this approach? In real life, do you think that different people have different trajectories? That when I presented the old model, I sort of said that beta 1 really is the slope for everyone. And if it doesn't look like it, it's just because we're measuring CD4 counts with some noise attached. But in fact, there is some truth beta 1, which is the effective time on CD4 counts, and everybody in the sample and the population that I've drawn from has exactly the same slope, and I just need to estimate what that slope is. Versus the story here, no, everyone's not the same. Everyone is unique. Everyone has their own starting point, and everyone has their own trajectory. Some people, CD4 counts may be going up, B1 may be positive. Some people may have CD4 counts that are actually going down over time, B2 is negative, and some people, their CD4 counts are stable, B3 is 0. Everybody is unique, and it's not just a matter of noise that they don't look the same. It's a fact that each person has their own particular unique characteristics that drive the relationship of their CD4 count to time. And not just the relationship to time, but where they start from is also uniquely driven by their biology, by their environment, by their behaviors. These are all different numbers, and we shouldn't propose that one number fits all. And so, I guess this is sort of the philosophical point. If I was in the room with you, I'd ask you to raise your hand and tell me, what do you think is a more reasonable approach? Everybody is unique. We cannot say that there's one effective time because individuals are not lab mice, genetically identical under identical conditions. Everybody is unique, and everybody will have a unique slope and a unique starting point. Or is nature not that complicated? Is there in fact one message that nature is trying to tell us, that in general everybody's CD4 counts follow this pattern, and if we're not observing that exactly, it's only because we're measuring CD4 counts with noise in our measurement? And so, are there any hands raised for this view of the world?
Yes.
Okay, I'm of this viewpoint too. I think this is much more reasonable. I don't know if you've talked about, probably you're familiar anyway with meta-analysis. This is exactly the same principle, the same philosophy that drives a meta-analysis. There, we're not looking at different people and their trajectories over time. We're looking at different articles that have been published. And from each article, we pull a relative risk that shows the effect of the intervention in that study. And we notice that all the relative risks from the different studies are not identical. Do you believe that, in fact, the reason they're not identical is because they're measured with noise? Or do you believe that they're not identical because the studies were not done the same way in identical people using identical dosages and regimens? Are they intrinsically different? And while they may center on some central effect, the different studies you're combining are unique. Most people have bought into meta-analysis saying that we're using similar but not identical studies. Each one is unique. And so, in fact, they use a random effects model to analyze meta-analysis. Here, we're doing the same thing. We're assuming that each patient is unique. They tell us about the starting value. They tell us about what's happening over time, but in fact, each patient is unique. If you buy into this philosophy, or I guess secondarily, even if you don't, but this is the only approach in your software, you'll be analyzing your longitudinal study using a conditional model. So this philosophy takes us to a conditional model. It's this viewpoint of the data. This is the equation where we assume that the epsilons are independent, but for each person, person 1, A1 and B1 show up at time baseline, 6 months and 12 months. And so the CD4 counts for person 1 are linked over time through A1 and B1 showing up at each time point. For patient 2, we have A2 and B2 at baseline 6 months and 12 months. So we still have correlation over time. But the correlation is not some assumption you make about the epsilons. The correlation comes automatically from the fact that the person has the same value of A and B at baseline 6 months and 12 months. So in this case, if you're going to run your software, you're not going to say what's the structure of the correlation matrix. It comes out automatically. The program figures it out automatically from the A's and the B's. How strong is it and all the rest is not something you specify. It's something the program will estimate as soon as you say, I want to run a conditional model. Unfortunately, there is a choice you still need to make. So I've been showing you this model where each patient has their own unique regression line. Both the starting point and the slope are unique to the person. However, I suppose maybe you want a world, philosophically, where each person starts at a different value. So they've had HIV for a different amount of time, they received a different regimen, and so their starting point is unique. But now under study, everyone's going to have exactly the same trajectory. So this is still a mixed model, but instead of random slope and intercept, we have a random intercept, but everyone has the same slope. This is not an unusual assumption or an unusual model to run. It'll give you different answers than the one above it. But again, it's a choice that you make. Should I declare both the intercept and the slope to be random? Should I declare the intercept to be random? But in my view of the world, the trajectory is going to be the same because these people are now all in the same study and being treated the same way. Or, for some reason, do you believe that everyone starts at the same value, but their trajectory is different because the medications they take, the lifestyle determines a different trajectory for each person. So a fixed alpha, but individual unique slopes. Okay, so you still have some say, even when you say I'm going to run a conditional model, a random effects model, random slope and intercept, random intercept only, random slope only. That's the choice you're going to have to specify. Whatever you think is reasonable. Again, it's not going to be a matter of proving one is more right than another. It's more what you think is a reasonable view of the world. Again, good news will be the answer doesn't change very much depending on how you approach this. So, if I use the full-blown model, beta 2 is my fixed effect, but the A's are normally distributed random variables. If you think about it, the A's form a distribution. Some people have higher values for A, some lower values, so their CD4 counts are higher or lower at the start. But those A's form a normal distribution centered at alpha with a certain amount of variability. And this is sort of the key assumption here, because when I get done running the model, there's 103 people. I don't think you want to show your reader 103 intercepts and 103 slopes and ask them to make sense of it. What you're going to show the reader are not 103 intercepts, but this mean, where are those intercepts centered? And you're not going to show your reader 103 slopes. You're going to show of the slopes that are normally distributed, they're centered at some value beta. This is the number that you're going to show your readers. Otherwise, the epsilons are independent, normally distributed. These are the usual assumptions. So we go from a unique model, if you like 103 unique models, to a summary of where the models are centered. And it actually works out, well, first off, pretty well. This is the model that I ran. This is what the results look like in terms of my printout. 502 plus 17.9 times time plus 6 times female. If you think back to earlier slides, this looks pretty much like what I showed you 15 minutes ago. Same intercept, pretty much the same slope, pretty much the same difference between men and women, with pretty much the same standard errors and the same p-value. And again, I consider that good news. I hate to have my answer depend on approach when I'm choosing the approach as much by philosophy as any sort of empiric results. So the fact that I get a similar answer gives me very good reassurance that this is a reasonable model. If you want to see where it got the 17.9 and the 5.86, the beauty with this model is I can do it for you. So when I ran this model internally, there's 103 people in the database, which means there were 103 intercepts. And here's the distribution of the intercepts. Here's a histogram. The intercepts are centered at 502, which is why the program printed out 502. Some people start with a CD4 count as low as 200. There's many people with 300, 400, 500 as the starting CD4 counts. And some people in this database have a CD4 count at baseline up around 800 to 900. If you like, 95% of the people were between 473 and 530, but my best estimate would be that in this population of people, individuals are centered around 502. So that's my intercept. More interesting is the effective time. And again, with this approach, there are 103 people, which means 103 slopes. They're centered at 17.9. That's the mean of this distribution. And so that's why you see 17.9 here. But it's very interesting. None of the people actually had CD4 counts that were going down over time. So if you looked at the slope for each person, everybody's slope is positive. Although for some people it's positive and very close to zero. So their CD4 counts weren't changing very much at all, or at best a tiny bit. Some people, they were going up by 10 or 15 or 20 units per month. Some people, the slopes were quite steep, 25 up to 35. And so you get a sort of interesting impression of what the slopes were. If I cut off 2.5% from each tail, I have a confidence interval. If I use the variability, I get a standard error and p-value. But you actually get to see not just a single number, but what's actually happening in this group of people. Reporting-wise, probably just 17.9, but you get an idea of how much heterogeneity, whether there were some people who were actually going down, whether some people who were going up sharply over time. It's a very sort of attractive model. And for all I know, maybe you want to take these 103 slopes and then do a regression on the slopes and see if men had more positive slopes than women. If people who had disease longer had lower slopes than people who had disease shorter amounts of time. You could actually analyze these slopes now as a secondary outcome. So the conditional models are a little bit unusual, takes a little bit of learning, but once you do, they're very attractive. And like I said, if nothing more than just running them, it's easy enough to interpret them. And my last slide is there. This was the result from the marginal model unstructured. I ran the conditional model three ways: random intercept and slope, random intercept but fixed slope, fixed intercept random slope. And if you compare them, the intercepts are the same, standard error is different. The slope over time is similar no matter how you approach it, with a similar standard error. And again, the effective gender is small, similar with similar standard errors. So choose a marginal model, choose a conditional model. It matters, but not a lot. Amongst the conditional models, what do you want random? Up to you. Doesn't matter, again, a huge amount, but it does matter a bit. So you can't go fishing around for the best result. But the good news is, no matter how you approach it, you'll come up with a reasonable answer, a similar answer. And that should be it. Oh, conclusions, summary. So if you have correlated outcomes, there's two main approaches: marginal model, conditional model. Marginal model takes the ordinary regression and says the error terms are correlated, and you'll need to specify how they're correlated. Unstructured would be simplest, but worst for power. Or you could use a conditional model where the correlation comes in through random coefficients, and you just need to specify which coefficients are random, the intercept or the slope. And the results are often, not always, but often very similar. And now, appreciate your attention, and back to any questions.
So if we were to look at longitudinal measures with subjects, whether, 100 and above, it almost intuitively becomes more convincing to me that we should be thinking of the conditional models. Because, I'm sorry, let me say one more thing. That's the whole idea of precision medicine, right? That we have randomized trial, we have mean effect size estimates, we assume, this is the average response, but we have responders and non-responders. What you're showing us in the second approach is that you're showing a more individual approach to response, if I may say that.
Oh, it's absolutely true. Very true. The question is where you're starting from. So we're doing a randomized trial. The treatment is regimented. The patients were chosen to be homogeneous. Do we really have individualized responses, or are you expecting pretty much the same response from everybody?
When we've done the trials I've scrutinized, I'm getting to realize more and more how variable response may be. A very quick example is a trial we published in 2 very good journals for insulin resistance and bone mineral indices, and we gave vitamin D high dose, low dose. So they all started at an average level, but the delta increase in vitamin D varied a lot within the low dose group and varied a lot within the high dose group. And I can think of other examples. So I'm really thinking that one size fits all is really not very good for biological variables. I may be biased, but what do we have to lose? Let me put it the other way. What do we have to lose if we were to use the second model? It's a bit more complicated, but it makes sense, and it allows you to look at dissecting your results.
I agree. Like I said, I had a personal preference for the second approach as well. It is, for linear regression, runs smoothly, not a problem. For binary outcomes, non-normal outcomes, it can be a little bit more difficult to find the software, and the software can be a little bit more unstable. Sometimes it won't give you answers at all. But assuming that it runs, everything you've said is sort of a strong argument for using this approach. So I agree with you.
Okay, great.
Can't argue. This is a Bayesian point of view, that there is not one answer in the world, that there are many answers.
Thank you. Any questions?
I was just wondering about.
Can you come forward? There's one question. She's going to come to the mic.
Sure.
So the question is about seasonality. Suppose that we're measuring influenza incidence per year, and then we realize that in winter time we have peaks. So do we introduce a variable for winter or the term, or how do we do that?
Yes.
Okay.
As long as you have more than one sequence. So if you had only 1 year of data, I couldn't help you. But as long as you had at least a repeat, so 2 years of data, we could either put month indicator variables for month into the model, or we could put indicator variables for season into the model. And you could either focus on those and sort of look to see how many more cases there were depending on which season, or you could just use it as an adjustment. So if you were looking for other predictors, you can take the seasonality out of it.
Okay.
So definitely you can put season into this sort of model.
And there will be an interaction term between time and seasonality, or no need for it?
No need for it.
No need. Okay. Thank you.
Yes, can you come to the mic? There's another question.
Yes, so my question is, if we are looking at the quality of care across different shifts, say over 90 days, same individuals will answer same questions. We're checking mortality also across time and between shifts. What would be my random effect here?
John, did you hear the question?
I think it disconnected. I'm gonna reconnect.
Okay.
Yeah, we got disconnected.
Yeah. Odd. Let me get my camera back on
Yes.
too, if I can. But I can see and hear you now.
Okay.
Okay, so I'm gonna repeat my question. We are looking at two different outcomes. We're looking at mortality and we're looking at, say, job performance. And we are checking those two outcomes over 90 days, different point in time, different shifts, like day shifts, say, over 30 days, and then same outcome collected during the night shifts over 30 days, and it's repeated for several months. So what would be my random effect here?
Okay, so this is all, it's frozen. Sorry, can you just repeat it one more time? I was trying to
Okay,
adjust
yeah.
the screen here, so,
No problem. So I said we
Thanks.
have two outcomes. We're looking at mortality and we're looking at job performance.
mhm.
And we are collecting those outcomes over 90 days. The occasions would be, first 30 days would be from the day shifts, and then the second 30 days from evening shifts. The third 30 days would be from the night shifts. What would be my random effect here?
For structure of your study, is this from only one workplace?
More than two facilities. We're having our sample is like more than 300 nurses. But if they are responding to our questionnaire over 90 days, we should get more than 3,000 responses.
Okay, I'm just trying to identify who the outcome is coming from. So if each nurse is supplying information,
Yes, this is for the job performance, and for the mortality is from the patient service administration.
okay, let's do the job performance first. So each nurse is measured multiple times over time,
True.
sometimes day shift, sometimes night shift.
Yeah.
And for each of those, you have her job performance.
Yeah.
And you wanted to relate it to which shift it's on? Is that the predictor of interest?
With shift, yes, and
Okay.
if there is weekend effect also.
Say again?
Weekend effect.
Weekend effect
Yeah.
as well. That's fine. So I'm seeing each nurse in your study the same as each patient in my longitudinal database. I only had them measured 3 times. You have each nurse measured many times.
Yeah.
And each time you measure the nurse, the outcome being job performance, job satisfaction, and each measurement is tied to which shift and whether it was weekend or not. So that's perfectly fine. Your question for this particular study,
Where's,
so I've got
where's my
300
random
subjects.
effect?
I've got my outcome and predictor. The correlation would be across the different measurements, and you have many measurements per nurse.
Yeah.
Okay. My only concern would, well, how many measurements per nurse do you have?
I have several.
Several as in
W-
5 or several as in
More, we're
500?
talking more than 20.
More than 20.
Yeah.
So, I mean, everything we've talked about is applicable to your study. The only thing that worries me is the 20 or above 20. If I try an unstructured data,
Yeah.
a correlation matrix, that's a lot of correlations.
True.
Autoregressive might be sufficient, or the conditional model would avoid a lot of correlation.
Okay.
But I guess that's the only thing that I can think of that's
Okay.
a hitch in your story would be whether an unstructured correlation matrix would be a good idea or not. But everything else that I've talked about works. Either model, marginal or conditional, would work.
Okay.
You're looking for within-person changes, so whether it's day shift or night shift is a within-person difference, or if it's weekend or not weekend is within person. If anything, you should be gaining in terms of power. And this is sort of classic panel data that you're describing, a classic longitudinal study.
Okay.
So, what was your question or issue with this particular
The
study?
random effect.
So, the random effect would be, I would put the random effect for the person, so an intercept.
Okay. Okay.
That means that each nurse has their own level of satisfaction,
Okay.
if you think about it that way.
Okay.
And that level of satisfaction can be lower on weekends, higher on day shifts.
True.
But if you sort of think about putting a line through a time graph, each nurse has this personal level and then varies around it.
Okay.
So with a random intercept, that should have no trouble running at all.
Okay.
It should have good power and give you sort of good answers about shift differences and weekend versus weekday differences.
Okay.
That shouldn't have any trouble running at all, actually.
Okay. Great.
That would be a nice example. What was the other outcome, though, besides satisfaction?
Mortality.
Not the nurses, though, I hope.
It's patient mortality. It's patient mortality, but we're trying to
Oh.
relate it to job performance.
So during that particular shift, how many patients died?
Well, we have aggregated data just for confidentiality, so we're just taking a rate of mortality per month on that specific unit.
Okay, but if it's per month, what's the predictor now? Or are you just interested
Job
to see if
performance.
there's the
Job performance.
job performance?
Yeah.
Oh,
Yeah.
and this is, but the mortality is across nurses, or is it for the patients seen by each particular nurse?
No, across nurses.
So it's aggregated.
It is aggregated. Yeah.
But job performance is not.
No.
Then you're not going, well, you can't do it.
Okay.
If the outcome is already aggregated,
Yeah.
I can tell you whether there's trends over time.
Yeah.
I can tell you if you aggregated the nurse's job performance, we could look to see if there's a correlation between aggregate job performance and aggregate mortality,
Okay.
so that in months where job performance was low, mortality was high.
Yeah.
But we cannot break this down to a nurse by nurse, the same sort of analysis anymore.
Yeah,
because
okay.
we don't have an outcome for the
Okay.
nurse.
Okay. Okay.
So aggregated, just a correlation coefficient is probably all you need, not a model, but just 2 columns of data, month by month,
Yeah.
the aggregate mortality and the average job performance, and run a correlation coefficient to scatter plot between them.
Okay. Okay. Good. Thank you so much.
Sure.
Hi, doctor.
Hi.
I'm working on a data set for longitudinal data, and the outcome is not normally distributed. You were saying that that some softwares are not powerful enough. So, what would you suggest to do?
What sort of outcome do you have?
So the outcome is a score from 0 to 6. And it's repeated measures, almost 1,200 measures.
Okay, and what does the distribution look like? Are people clustered near the 0 end or the 6 end?
No.
No, they're in the middle of the scale, or?
They're like there are all sort of distributions. So because like it was like the spaghetti plot you showed us last time. So I had like all sort of lines when I did the scatter plot.
Okay. So you're measuring people multiple times,
Yeah,
but each time on
5
this
times.
0 to 6 point scale.
Yeah, 5 times.
5 times.
Yeah,
But each time 0 to 6 points.
yeah.
How
Yeah,
do they get the
but
6
yeah,
points?
when they get the 6, we assume that whoever gets a 6 would not go back and get a 5.
Oh,
Yeah, so it depends on which wave they reach the 6, but we assume that some of them would get the 6 at a slower rate and some of them at a faster rate.
okay.
Yeah.
Is that the goal, though? Is 6 sort of a perfect score and you're training them to reach
Yeah,
6?
yeah.
What about doing this as a Cox regression instead?
I thought about it, but and it's not the time. We're not measuring like the time to get this. Would that be a problem? We're not measuring like the time to get this score.
Well, in a way you are, because you said you stop measuring once they reach 6.
Yeah.
So, that's going to be the problem. If we analyze this as repeated measures,
Yeah.
once a person gets to 6, they drop out of the sample.
Yeah.
It'll be the opposite would be a healthy survivor. So if you were measuring blood pressures and it went high enough and the person died, you wouldn't see them anymore. And so the people who came for the next measurement are all healthier because the dead people have been removed. Here are the people that do the best, basically are dropping out of your sample, and the people who remain are the ones with the lower scores.
Okay.
It'll be very hard to make sense of that.
And doing the Cox regression for longitudinal data, so that's another, like, is it similar to what we talked about today? Like, is it like a normal Cox regression, or?
Yeah. It is. This would just be a normal Cox regression, because although you have repeated measurements,
Yeah.
each person's outcome for the Cox regression, there's just one outcome. How long until they reach to 6?
Oh, okay.
So it would no longer be longitudinal, it would just be a standard Cox regression.
Oh, okay.
As we talk, I'm sort of thinking about it. If you did it, so if you did it as a longitudinal, I'm trying to think, it still wouldn't be bad as a random effects model. I'm tempted to leave it as a linear regression even though it's a 0 to 6 scale. If we just did it as a linear regression, and you had random slopes,
Yeah.
then basically each person's slope reflects how quickly they got to 6. Even if they stopped after that, you would still get a slope for that person. And the people who got to 6 quickly would have steep slopes. The people who took longer would have lower slopes. And so if you ran the random effects model, saved the individual slopes, they'd actually be pretty informative. It's basically how much time they took to get to a 6. Maybe it gives you more direct information than the Cox regression would. So I would not be tempted to switch models from linear. There are alternative outcomes, but they're going to be harder to interpret. This basically, like you said, it would be the spaghetti plot. Everybody is going to be going up either slowly or quickly, and really you just want the slope. So it's not so much the distribution of the outcome, but the speed with which they reach the 6. So I guess I would do it the same, the random effects, random slope, and save those slopes as sort of the interesting part of the outcome.
Okay, thank you very much.
Sure. Does that make sense? Or
Yeah. Actually, I tried doing something like that, but doing trajectories and grouping, grouping these people into groups using the trajectory command on state. But I didn't know how to interpret it very much. So.
yeah, I'm not sure of the trajectory command. But if you do run it as a random effects, it might be exactly the same thing. You really will just get slopes for everybody.
Yeah. Okay, thank you.
Okay, sorry.
Thank you, doctor. We have no more
Okay.
questions. Thank you.